Okay, so hello everyone. Welcome to the fifth lecture. So we are one third through, I guess. And last week, what we did last week? Ah, yes, of course. We did a crash course on stochastic processes, theory of stochastic processes, and we practiced a little bit. We practiced a theory on the example of random telegraph noise, or RTN. RTN, right? Random telegraph noise. Random noise. And yeah, that was all we did last week. So this week we will apply what we learned to some dynamics of quantum systems, quantum states. So as title indicates, we'll talk about stochastic dynamics today. So what is stochastic dynamics? So I will say that the state, the quantum state, undergoes stochastic dynamics when the density matrix at time t equals time ordered E minus I integral generator S ds acting on rho at time 0 and and all this is bridged, okay, or in more explicit terms, I will explain everything in a second. HFS, sorry, HF SDS integral the distribution, functional distribution of process F, dF, and this super operator acts on initial state. Okay, so this is like an averaged unitary dynamics, let's say, where the generator is a stochastic superoperator. So it has a standard form of a commutator with Hamiltonian, right? And this Hamiltonian is a Hermitian but stochastic operator. Stochastic Hamiltonian. So it's stochastic because it depends on process f of t. Okay, so we have stochastic process f, which has probability distribution, functional probability distribution pf, right? And we have a Hamiltonian for our system that depends on the stochastic process, which makes it a stochastic Hamiltonian, and it generates evolution by taking the exponent and averaging over realizations of the stochastic process. So that would be the, let's say, definition of our stochastic dynamics. I will use a shorthand notation. Shorthand notation. So if from context it's clear what kind of Hamiltonian we have and what stochastic process we are dealing with, I will use symbol like for unitary maps we use U, so this will be U with a bar, and this is by definition it will be this averaged. It's this guy, right? Or if you want full form, H, F, S, T, S, P, F, F, D, F. Okay, and I will call this guy this stochastic map. So we had unitary map, now this will be a stochastic map. Although after everything is averaged, it's just operator, it's no longer a stochastic variable or process, but the name is okay. Sorry? Ah. Yeah. No, wrong. Yeah, sorry. No, what maybe I shouldn't write, so I'm making fool out of myself. Stochastic, right? I think it's more correct now. Those probably still not super correct. Okay, so that would be a definition. And those stochastic maps in literature, there's sometimes U bar is called they call it random unitary map. That's how they call it sometimes in literature, and this is also a good name, right? Because if you look at this, if you look at U bar, you see you have each guy here. Each guy here, each exponent here, it's like it's a unitary map for fixed trajectory of the process. So it's like trajectory-wise unitary map, right? Because once you pick some trajectory, you pick a trajectory, right? This is just a function. So you just input it into your Hamiltonian, then it's just normal time-dependent Hamiltonian, nothing stochastic about it. So time-ordered exponent of it behaves just like a unitary map, and you average it with the probability distribution. So the name is pretty apt, right here, because it's like unitaries that are averaged over some stochastic variable, stochastic process. So that's nomenclature. All right, but of course the question is, definition, but why, right? What's the motivation for actually using this guy, or is there any motivation for using this? And there are a couple of reasons why you might want to or need to use this kind of description of dynamics. The simplest to understand and to explain at this point would be a situation when, okay, imagine we have system when we prepare it, right? We prepare the initial state, and we also like prepare the system as a whole. and this the Hamiltonian of our system depends on some external potential, some external field. But the problem is that in each run of our experiment, we don't really fully control what's going on, and this external field changes from shot to shot. Okay, and we just don't know what's going on there, like on the microscopic level, but we know some probabilities. We know a probability that this field would be f of t. Okay, we have the probability distribution. So in each shot, when we do our preparation and the measurement, we can explain everything with a state that's dependent on a given realization of this external field. Right, so we would have a given trajectory inputted here, right? So in each shot, any experimental results can be explained by setting up this kind of state. So, for example, a expectation value of some observable. So we would have expectation value given the field f. So we would just take standard formula rho t of f, right? Something like this. But now the issue is we don't know which realization actually occurred in any given experiment. We just know the probability distributions. So we have this uncertainty here, right? So when we run our experiment many times to actually collect the statistics, to compare them to expectation values that quantum mechanics tells us how to calculate, we have to incorporate this uncertainty. So the actual expectation value for us would be, expectation value would be the expectation value conditioned by the realizations of field times probability distribution of getting any given trajectory of this external field, right? But this, if we write down what it means, so we have trace, we have operator, we have rho TF, PF, F, DF, right? But that's nothing else but a TH minus I integral H for a given trajectory F, small f, rho 0. Everything is averaged. And that's just trace A UT0 bar rho 0, right? Like I can average the only thing depending on the trajectories on the process are the evolutional maps. When I average them, I get my stochastic map, right? So this would be a one scenario, right? So we have external field. We don't know, there's uncertainty about this field, so we model it with a stochastic process. We incorporate this uncertainty, and then it's straightforward reason why to use this formalism of stochastic maps. But this is like the most simple reason, the most primitive, and perhaps most artificial out of all of them. There are other reasons, more like more natural, let's say. But to fully explain what are the mechanics what are the mechanics behind them, we first have to go through essentially the whole course, okay? Because it's sometimes it's possible to, when you have two interacting systems, one of those systems can be made to behave as if it was this like stochastic process, this external field that behaves randomly, okay? But to get there, first we have to understand how to deal with interacting systems, which means we have to develop the theory of open quantum systems, and then figure out, okay, what kind of limits, what kind of dynamics could lead to this kind of reduction. And this, we will explain it, but it will be at the very end of this whole course, okay? So it's kind of advanced idea, but stochastic dynamics, so it can be either really you are modeling some external noise given by your experimental setup where there's some uncertainty, but more often, more naturally, it's just a kind of, let's say, approximation of a real quantum systems interacting with each other, okay? So it's like in classical mechanics, we often do the same thing, right? You have a planet orbiting sun, right? And you like, so two body problem, right? But it's possible to like eliminate one body, sun, for example, because it's massive, probably doesn't move much. So you just look at the planet as if it moved in some external gravitational field, right? And there can be some noise in this field. So you would then model it with some stochastic processes. But this is like you feel it, right? You have many body problems. Sometimes you can reduce it to one body in external field, okay? So this idea of stochastic dynamics essentially boils down to similar thing, but in quantum mechanics. Okay, so it's more fancy and more complicated, essentially. But we will explain it, but at the very end of the course. Okay. Hope it was clear. So that would be the motivation why you use it. So I guess a thing to finish this off, this introduction would be to actually prove that this stochastic map is actually is a well-defined thing, that it takes density matrices and is actually evolves them into density matrices, okay? Because we want to have evolution of state. So we don't want to break anything along the way. So we would have to prove no. So this leads us to assignment 21, which we'll do right now. Verify that stochastic map is a proper map from density matrices to density matrices. That is, check if rho of t is positive and have unit trace, right? So so that it still can be treated as a density matrix. And it's a simple enough calculation, straightforward stuff. So assignment 21. Okay, so first, let us show that U bar preserves trace. So we want to calculate trace of rho of t, okay, and we want it to be the same as trace of the initial density matrix, which is 1, right? So if we just put in our stuff, so that would be a stochastic map acting on rho 0, sure enough. The stochastic map is we already did this trick. So it's like a unitary map for each realization of the process. So trajectory-wise unitary map. and everything is averaged over the realizations, right? But we already know, we checked that before on previous lectures, that unitary maps, this is unitary map, even I can add it trajectory-wise, unitary map. And we know that unitary maps, they preserve trace. We already checked that. So we have trace of row 0, and the F. Probability distribution is normalized, so it's just trace of 0, which is 1, by the way. So this is good, it's trace preserving. Does it preserve positivity? So the second point is to show that preserves positivity of, or you just say that it's a positive, is a positive map, which means that it preserves positivity. It's also straightforward calculation. So we take our stochastic map acting on row 0, but this guy is again unitary map, trajectory-wise unitary map acting on row 0, and row 0 can be, because it's row 0 is positive, so we can use this representation as a product of square roots, right? If you recall from previous lectures, PFF, DF, and remember this guy is non-negative. Probability distributions are non-negative. So in particular, a square root of PF is well defined. Okay, so we know from our previous calculations that this guy, if this is unitary, we know that this form will be preserved. So we can write it as, let's say, like this, dagger. Okay, because unitary maps, we checked this previously, okay? It will preserve this form, but it will, this operators, the square roots of row of the state of the density matrix will depend on the on trajectories, right? Lost my guide. Okay, here it is. But again, it's positive, so I can like incorporate it even further. You can write it like this. PF. Just split it in two. And DF. So we have this form characteristic for positive operators. The integral doesn't bother us because it's just a sum of positive operators. So everything is positive. Okay, so it is a correct map. It is a proper map. Okay, I see. I lost my place. All right, so that's ends our assignment. So next thing, what do I have? Okay. The next thing, 3.3. Stochastic maps and joint probability distributions. So on previous lecture, right, when I introduced stochastic processes, right, we said that, you know, the process is defined by this functional probability distribution for the trajectories of the process, right? But I said that it's equally well, you can describe your process with a, rather than this one master probability distribution, you can like have whole family, infinite family of multi-time probability distributions that are normal functions, standard functions, not some abstract functionals. So if you remember, we had these guys, and we use the tuple notation. So n is like any natural number, and the times are supposed to be ordered. And let's write it like that, right? So these guys, these were standard probability distributions, and we call them joint prob distributions, right? And I advertised that all practical calculations and stuff like that, you can abstract proofs, maybe you can tackle with this functional probability distribution, but all practical calculations, you do it with those joint distributions. And we investigated some of them, how they behave on an example of random telegraph noise. If you remember, it had some nice properties. For example, it factorized, because it's for Markovian processes, they factorize like that, and so on and so forth. So how those guys enter with our stochastic dynamics, stochastic maps? So first thing first assumption. So stochastic map is generated by a stochastic Hamiltonian, okay? And in particular, throughout those couple of lectures, we will be talking about stochastic dynamics. We'll talk about Hamiltonians of this form, the following form, okay? And some V. Okay, where this guy and this guy are just some constant Hermitian operators. Okay, H0 is a constant operator, V is also constant, so they are not stochastic in particular. The dependence on the stochastic process goes from like this. So it simply multiplies, the stochastic process simply multiplies operator V, and you can like lambda would be like a coupling strength. You can think of it as a coupling strength. Okay. So this is a specific choice. Okay. So in particular, we won't be talking about more fancy stochastic Hamiltonians. So we won't talk about. We won't talk about, let's say, a Hamiltonian that actually depends on a couple of stochastic processes. So for example, something like this, J, X, Y, Z, lambda J, Fj, some Vj. We won't talk about that, okay? Although it's a valid stochastic Hamiltonian, but we just won't touch it. And we won't touch stuff like this, where you have your dependence is like non-local in time. So what I mean by that, so we won't be touching anything that looks like this, for example. So you have f of t and here's some V that depends on time, and you do something like this. It's like time delayed dependence, stuff like that. We won't talk about this either. Okay, we just focus on these guys because it will be enough. Okay, it will contain all the properties, all the behaviors that will be like emblematic of all things you can like expect from this kind of evolution. And most importantly, the lessons learned from this, from investigating stochastic dynamics based on this kind of simple Hamiltonians will transfer further on, okay, to when we go to actual topic of this lecture, the open systems. So those guys we want to talk about. And now, once you decide on this form, you can actually, now you can show that description in terms of joint distributions is just straightforwardly natural for this kind of problems. And to see it, so let's take a stochastic map. So we have our stochastic map. With Hamiltonian given by this form, okay? And everything is averaged. And let's switch to, because our Hamiltonian, right, it has those two parts. So just asking for switching to interaction picture, right, to use the disentanglement theorem. So we can disentangle it. So we can disentangle the H0 part, right? And we'll be left with, let me write it like this. Lambda F S, so the process and the super operator V in interaction picture. And the average touches only this part, right? Because H0 is independent of doesn't depend on the stochastic process. So it's from the point of view of averaging, it's just constant. You can just put it outside the sign of averaging. And the generator V, the interaction picture is defined according to standard rules. S V 0S. Okay, so if you recall in like lecture number 3 or 2, I don't remember exactly, was one of the assignments was to like show this disentanglement for super operators, and this is where this comes from. Okay, so now we take this guy. Let's use our notation for this guy, for this interaction picture. And once we have it, let's just expand the exponent into a series. So plus n1 to infinity minus I lambda n. We have time ordered integrals to ds1, and we have our generators Sn times Vsn F S1 V S1, and everything is averaged. Okay, so we just expanded the time ordered exponent where the generator is V times F, right? But this simplifies immediately. Identity is not, of course, it's constant. Stochastic processes are not super operators, so we can move them around as we wish. They commute, in other words. So all these things as one average, and we have the super operators. So we recognize here that these are moments, moment of process f of t, okay? And if you recall from previous lecture, moments can be calculated using joint probability distributions, because you take moment like this guy. It's on one hand, it would be defined by average with the functional integration. That would be like the formal definition, but as we discussed in the previous lecture, you can also write it as a multi-time average with a multi-time probability distribution. So Sn, F, N, okay? So in this sense, actual calculations, actual computations are still done with those joint probability distributions. We reserve functional distributions for some, proving theorems or some properties, right? Practical calculations, you just use your guys, normal functions. Okay, so everything is under control. Yeah. Okay, let's have a break. Couple of minutes of break. Maybe like. All right, so let's carry on to the example. Maybe more interesting stuff. So the setup. Let's first a setup. So we'll be considering here a arguably very, very simple, maybe the simplest kind of model. So this will be a two-level system or a qubit that is driven by random telegraph noise. Okay, so the Hamiltonian I have in mind. So superscript q, because it's qubit. Okay. So it's stochastic because it depends on, this is RTN, okay? And it's time dependent, but its form is this, sigma z, okay? So it doesn't have this H0 part, okay? It's only the operator multiplied by stochastic process. And sigma z, just as a refresher, is a polymatrix. So it will be defined that in a basis B, okay, because the matrix depends on what basis you use. And we'll be switching between bases all the time. So B is a basis made out of eigenvectors of sigma z, which I will denote as up, spin down, okay? Qubit up, qubit down, whatever. And in this basis, the sigma z looks like this, it's diagonal matrix. Okay. So this is nice and simple, sure. And now, this Hamiltonian because it's simple like this, it has the property that it commutes with itself. HQ commutes at different times. Maybe I should write like that. Different times. So it is a time-dependent Hamiltonian, right? But it's the dependence on time is very simplistic, so that HQ are T, commutator HQ are T prime. This is 0. Okay, they commute with each other, so you can reorder them as you wish. So hopefully you can see, right? You can see that it does, right? Commute. And if Hamiltonian commutes like that, it automatically implies that the super operator, the super generator, also commutes. So if I take HRT, which is, commutator, it's called adjoint super operator, I think, when you take some operator and take a commutator with it as a super operator. I think they called it adjoint super operators or something like that. So this will be generator for our map, for our stochastic map, right? But it also commutes at different times, which maybe add Q just to distinguish it, which we can straightforwardly check that it does commute like that. So let's take composition in one sequence. You know what? Let me be more explicit about what we are getting here. If I just put in the HQ, right? I'm getting, right? It's R, so the time-dependent part just multiplies it, and you take commutator of sigma z, or maybe even 1/2 sigma z. So it's like a spin operator, 1/2, and let's get rid of this guy. And let's call this super operator SZ with a calligraphic font, okay? Because we'll be writing it all the time, everywhere. Okay, so we want to show that calligraphic H commutes with itself at different times. So we take a composition like that. So this is just lambda square RT times RT prime, right? And SZ times SZ, right? But this is, I can just rearrange it again, lambda R T prime as Z, lambda R T as Z, which is HQ R T prime, HQ R T, right? Which means that HQ R T, HQ R T prime minus HQ R T prime, HQ R T equals 0, right? So it commutes. This is how you show that it commutes, which is super helpful to us because it means that time ordering is unnecessary, right? Because ultimately, these are just generators. So time ordering is unnecessary. Or maybe it's not unnecessary, just does nothing, okay, for our exps. So in other words, this guy, THQ E minus 0 T HQR SDS average, it simplifies to simply minus I lambda R S DS SZ everything averaged. Is it clear? Because it commutes, right? So the time ordering does nothing here. So or we can also write it to be super explicit, and 1 to infinity minus I lambda n 0 T R S T S. So like integrated process power n S Z power n, right? And average. And factorial, because this is just a standard text. All right, so it means that provided that we can actually diagonalize SZ, right? If we can diagonalize this SZ, we can just have a calculate this exponent analytically, right? Because it's if you recall, right, a couple of lectures ago, we discussed that about computability.
The average is the exponent inside or outside of the average?
Exponent is inside. Yeah, it's yeah. This is very important, right? It's over everything. Okay.
On lower platform.
Well, once you do the expand it into a series, right? This is what it means, right? It's just the only thing that it touches is R. Like the absorbing average into the how do you call wykładnik? Just exponent, okay? Exponent of the exp, right? Like absorbing average into the exp. We'll be doing that, but that's another thing, okay? So this is like the average over everything. All right, so diagonalizing SZ. So this brings us to next point. Matrix representation. So at some point I promised I will talk about matrix representations for superoperators, and this is the moment when we come back to this stuff. So we have bases for our cat space, right? Just to have it. We'll be referencing this later. And now, if you remember, the space of operators is also a vector space, right? And you can make a Hilbert space out of it by endowing it with a scalar product. So the scalar product for operators the standard choice is to have a trace scalar product. Okay, so that would be this is a standard choice for our Hilbert space of operators. Right, so we have vector space with scalar products. So if we want to talk about matrices, we first have to choose a basis, some basis in our vector space, which is, and we can choose the orthonormal basis because it's usually the best choice, right? We know what orthonormality means because we have scalar product, right? So it's all coming together. So what kind of basis we will choose? So a good first, if you have basis in your cat space like this, you can made out of it a basis in your operator space. Okay, so this would like the good first choice. So let's call this basis. So B, but fancy font, and you can make it out of those cats by constructing all possible projectors and coherences, as we call it in business. So projectors, so that would be a projector on up state, projector on down state, but you can also have like coherence. So like this, and it's Hermitian conjugate. Oh, sorry. So this is like the first choice. If you don't have any other ideas, this is how you can construct basis for your operator space. And it's like qubit, so it's two-dimensional space for states, for cats. Operators on this space are 2x2 matrices. So you need 4 entries. This means that your basis will have 4 elements, right? 2 elements for cat space, 4 elements for operator space. In other words, if your dimension is D for cat space, here will be D squared. Okay, D times D. So it grows pretty fast, right? Exponentially fast. All right. So the
Square.
yeah, D times D squared.
That's why you would be able to be to the power of the power of D.
Semantics. You know, it grows as square. So how do you call it when it grows like with?
Maybe just honestly, I don't know in English. Or usually it would be just square.
Okay. Okay.
When we have like this, for example, D is equal to 3, we would be having like 8, right? Of those.
Oh, 9. 3 squared.
Okay.
3 times 4. Yeah. 9. It's like, we have matrix D by D. We need D square elements to span the matrix. So you can imagine that each field in the matrix, it needs its basis element to represent it, right? Yeah. So let's use it to decompose some operators then. Let's start with the initial density matrix. It will be useful sooner or later, right? We have to be able to write it. So initial density matrix is an operator, right? So on one hand, you can it has this matrix representation when you let me correct myself. So on one hand, you can just take multiply it by identity from left and right, right? and then each identity you can decompose, let's call it like this, in B. Right, that's the composition of identity. So you take projectors onto, you take bases in cat space, right? And you write identity as a sum over all the projections on each basis vector. So 0. You do the same with the other guy, E prime. Right? This is how you arrive at the standard matrix representation of operators, right? So you have E prime belonging to B. You have E row 0, E prime, right? And you write it in a matrix form then as, so we have two bases up or down, right? Two bases vectors. Right, so this would be a matrix representation in a basis B. But this is like standard way of writing it. We treat a density matrix as a operator, but we can also treat it as a vector. This is where basis, this calligraphic B comes in, because the decomposition of identity, which we used here, is true for any Hilbert space. Okay, if you have scalar product and you have vector space, you have bases, you can decompose identity in this fashion, right? The trick is just to identify what this projector means. What is cat, what is bra, all right? So clearly in our vectors, right, correspond to operators. So these are operators, right? So vectors would correspond to operators, right? But what is bra? This corresponds to what? Okay. If you think about bra is simply it's a dual vector if you want to be fancy, but ultimately you can just, this is the left argument of a scalar product, right? So you can imagine that it's something like this, right? Right? So this is what bra means. It's like you take a 1/2 of the scalar product, right? So we can do it for our operator space as well, right? So we could write it as E like this, trace E dagger. Okay, and this is something we know how to act with on operators, right? And this is in fact, so this is vector cat, this is dual vector bra. So this would be a vector in our operator space, and this is dual vector in our operator space, which explicitly is just a 1/2 of the. So it becomes a super operator then that is a 1/2 of the scalar product. And all this means that if identity the composition of identity in vector space was this. The composition of identity in our operator space will be E will be this. All right? Which means now we can just use it to decompose our operators and superoperators into matrices. So with this revelation, we can take our density matrix, act on it with identity, so a bullet, and do the decomposition. Right? Row 0. But this is something we can actually just calculate. Trace E dagger row 0. So this is something we can calculate. We know how to do it. And times E. And once we recall what those operators E are in our case, these are just those projectors and coherences, right? So we can just substitute them. So we will have let's say, maybe let's be explicit. So trace up, row 0, up, plus trace down, row 0, down, plus trace. So we have up, down, but dagger. Okay, so it will turn into down, up, actually, upon taking a dagger. Up, down, plus trace. So down, up, dagger, row 0, down, up. So these are our basis elements. These are coefficients. In other words, we can now write it as a column vector, right? So this coefficient, this just turns into this. This coefficient down, row down. This coefficient is up, row 0, down. And the last one is down, row 0, up. And just to remind us that this is using the basis calligraphic B. Okay, so, and both of those statements are true. This is true, and at the same time, this is true. Okay, this is just different. You just treat them as different objects, either the operator or a vector. All right, so the real deal, because we want to check if we can diagonalize this generator, or as the non-trivial part of generator. Where is it? Okay, so we want this as Z, right? Which is just to remind us 1/2 sigma Z adjoint to sigma Z, right? And we want to see if we can diagonalize this guy. So we want to calculate its its matrix representation, which means, again, you put it as Z identities, right? You write your identities, you decompose your identities into cat brass, E trace, E dagger, bullet, SZ, E prime, E looks nasty. E prime, dagger, bullet. Okay. And this means you have sum over E prime, elements of bases, and you will have here coefficient. So trace E dagger, S Z acting on E prime. So we have here a super operator SZ, right? And it has operator on its right side. So we know how this acts, right? It will turn into some transformed operator. Then it is consumed by this super operator here, just pops in. So this is what I've written here. Multiply them, the result of this action of S, multiply with E dagger and take a trace. And this is a number. So this is a coefficient. This is a matrix element of SZ. And you are left with dangling, this dangling construct here, right? Okay, guy like this, but this is equivalent or corresponding to, you know, thing like this from standard vector spaces, right? So this just tells you, so this is a coefficient, and this is the entry in the matrix, right? Where the coefficients goes. So in other words, we could just list everything down, and I won't waste time for writing everything here. I will just show you what you get after you write it. All right, so as you can see here, you can arrange it into a matrix. So you have a Z acting on, say, projector, multiply it with projector, take trace. And this is like, so you need, and this is like elementary algebra at this point. And once you do all the algebra, which you can do it on your own if you are interested in seeing how it works. But what you get in a result that almost everything is zero, except for those two guys here, for this guy and this guy, which gives you 1 or -1. Okay, so this is a matrix of our SZ, and as it turns out, this basis is already diagonal, so we don't have to diagonalize it manually. The basis we just chosen as a default turned out to be the best choice because this is the basis that everything is diagonal in. And this is a good news because, you know, this is a 4x4 matrix. And in general, those guys are not always, it's not always possible to diagonalize them analytically, right? So if you get diagonal form for free, just take it and be happy, okay? Because it's not always easy to find it on your own. Okay. So let me write this guy as a matrix. So it's 1 minus 1, and everywhere else is 0. Okay, this is just nonsense. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1. Okay. In basis B. Okay, so once we have this, now we can easily compute the stochastic map, which is just EI lambda TRS TS SZ and averaged, everything averaged, which because we have diagonal form of SZ, this just turns into E minus I lambda integral of R times 0 eigenvalue, right? E minus I lambda integral of R S ds times 0 eigenvalue, is average, minus I lambda RSDS times eigenvalue 1 averaged, and blah 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 eigenvalue minuses. Okay. Not enough room, sorry. And 0 everywhere else. In other words, this is just 1 exponent of 0 is 1, and here we get minus I lambda TRS ds average plus I lambda 0 t. Average, and 0 everywhere else. So it's a diagonal matrix, okay? And just for the sake of convenience, I will call this boy here W of t, okay? In a business, it's called coherence function. Coherence function. And in a second, I will explain why this particular name. So we have our matrices. So now we can just act. I mean, we can evolve our initial density matrix to time t. We have our matrices. We can just multiply them, vectors and matrices, and obtain the result. So rho of t equals on row 0, right? Which is on the one hand, 1 WT conjugate WT. And on the other hand, we have our initial condition. So a word of caution here, to do this multiplication, you have to choose the same ordering of, which basis element correspond to which place in your matrix representations. Okay, if you choose some different order here and here, then here you will get some nonsense, right? So just be careful how you arrange your matrices, which you can arrange as ever you wish. Just be consistent. Okay. All right, so this multiplication is quite easy, right? Because the first two elements are unchanged. And the other two are just multiplied by corresponding W. Here W conjugate, and here just W, right? Or going back to our, cat space, you can rewrite it as WT WT. But this is in basis not calligraphic B, right? Right? You can have all those different forms depending on what's more convenient. You pick your form. And now, so in this form, maybe it's much clearer why it's called coherence function, because it multiplies the coherence. Okay, because this means the off-diagonal elements of density matrix indicate that there is a superposition, right? So there is a coherence. Your state has coherence, and your evolution just modifies only this part, only the off-diagonal part of your state, by multiplying it with function W, and that's why they call it coherence function. Yeah, okay. So that was a matrix representation. So as you can see, this is like super operators, so scary, but it's it's just bigger matrices, nothing more, nothing less. It's just the same old stuff, right? You just have to realign a little bit your way of thinking, right? Set your mind free and just think of super operators as matrices, and all the tricks, all the maths can be applied here as well. All right, so to fully analyze what's going on here with this our simple model of qubit driven by this random telegraph noise, we identified that the only thing that's happening is those W functions. Actually, this W function, W of t. If we understand how W works, we know everything about our evolution, right? Our model. So let's analyze it a bit then. Coherence function. Next step. So coherence function W simply I lambda 0t and the stochastic process integrated. So it's just a number, right? It's just a number. But we can write it, expand the exponent. Oh, sorry. I forgot the most important thing. It would be super trivial, but there is average here, right? This is what makes it non-trivial. So we have our plus, sorry, n divided by n, 0t dsn, rsn, rs1, average, okay. And there was this little tiny nuance about probability distributions, that we defined joint probability distributions only for ordered times, okay? So one small thing we have to do here to actually use our joint distributions, we have to order the integrals, which is trivial thing to do here because everything, stochastic processes are numbers that commute with each other, so there is no difficulty here. We just lose the n factorial. This one. And this guy, finally, we can just remind ourselves that we are using random telegraph noise here. But so far, we haven't used any properties of random telegraph noise. We just are like arbitrary, behave as arbitrary stochastic process. To n r n r1 p r s n r n. Okay, so this is W. If we can calculate this, and we know we can, because this we on previous lecture we were able to find the analytical formulas for moments, so we know how to calculate them. So you might think that, okay, so just substitute the formulas we obtained previously, and then maybe we get do the integrations, and maybe we'll get something that is familiar enough to some serious expansion of a function we know, and we can just go back to some analytical expressions. And this might work, but actually telegraph noise, this coherence function for telegraph noise, it can be calculated in more clever way, okay, than just expanding everything in series, substituting moments, and then converting back into the function. There is a more tricky solution to this problem, and I will leave exploring this more tricky solution. I will leave it as an assignment for you. So let me jump to the bit. So there is assignment 22, okay? So it's calculate coherence function for random telegraph noise. And, there is a whole description. The method is described here. Just take a look at it and see what you think. But after everything is said and done, the result of your calculation will be that W of t is given by the following formula. So it's E minus small wt. So this is if you recall, so telegraph noise has only two values, one +1 and -1, and it switches with some rate, small w, right? This is like the fundamental constant that defines the process. So this is this w, the switching rate. So you have this exponential decay, and then it multiplies hyperbolic cos. So again, this wt, and the frequency is minus lambda square w square root. Okay, so lambda is the coupling strength. So lambda is here. Okay, it multiplies how strongly the process is coupled to our qubit. W is again the switching rate. So you have this here a ratio between those two. Then you have plus W plus I, so imaginary unit, P lambda. This P, parameter P, it defines the initial condition for for random telegraph noise, if you recall. The first probability, single time probability, is like parameterized with this P. Okay. If you remember, then divide everything by W square minus lambda square, take square root, and hyperbolic sine, WT, and the same frequency. That's the formula, and which can be obtained analytically with a clever tricks that work because this is a random telegraph noise. And just a word of caution here, maybe not a word of caution, but to spoil the fun. So this kind of thing, the exponent of integrated stochastic process, we call it coherence function, but it's also in a abstract mathematical theory of stochastic process. This kind of object is kind of important. They call it characteristic function of a process. If you have it, they say you have everything. It's like another equivalent way to describe a stochastic process. If you have this characteristic function, you can like figure out everything about the process as well. And but there are only precious few processes for which you can actually calculate it analytically. So the fact that we have here a formula, closed formula, that actually looks kind of not monstrous, it's a it's a 1 in a million event. Okay, it happens not very often. Okay, there are a couple of processes for which you can calculate this guy. Random telegraph noise is one of those guys. In general, don't expect to get analytical formulas for this kind of exponent. Okay, it happens very infrequently, but here it actually happened. And the things to note about it is like, as you can see here, this ratio. If rate is larger than coupling strength, this is a smaller than 1, right? So it's just 1 minus something smaller than 1. You get a positive number, square root does nothing, it's okay. So we have exponential decay that the obwiednia, how do you call obwiednia? Goddamn, I forgot the word, obwiednia. So we have some hyperbolic cosine function, hyperbolic sinus functions that are like damped by a exponential decay. But now, if actually lambda is larger than the rate, this is bigger than 1. And then you get here a negative number. It takes square root. So it turns into imaginary, if this frequency takes into imaginary number, which then transforms hyperbolic cosine into just trigonometric cosine, right? And same for trigonometric sine. So you get like this oscillatory behavior instead, still damped by exponential decay. Okay, so there are like there is maybe a phase transition, let's say, for random telegraph noise here, depending on the ratio between the rate of switching and the coupling strength, you get this either oscillatory behavior or, well, this other behavior without oscillations. But whatever the case, the long time behavior of W's, you can investigate it on your own. But as time goes to infinity, you get either exponential decay. This is true when lambda is larger than W. So when there are hyperbolic sine and cosine turn into oscillatory guys. Or you get e to minus W times, I wrote it like 1 minus 1 minus lambda square w square root times t. And this is when you have this other behavior, okay? So you have like, either you have a clear exponential decay or you have exponential decay with some renormalization of the damping constant. Either way, it goes to zero as t goes to infinity, okay? But this means that our density matrix, which, you know, let's recall down. So we had W here, T rho 0, WT down rho 0 up. So this guy, as time goes to infinity, the off-diagonal parts just disappear. All right, so we'll have to finish soon. Actually, yeah, right now, we'll have to finish right now. Just one more note here. So this means, the coupling to this random telegraph noise, this qubit, it over time it erodes the off-diagonal elements of the density matrix. But this means that unlike unitary evolution, where if you start with a pure state, you will always remain pure, right? If you start with mixed state, you will always remain mixed to the same degree. This stochastic dynamics, it can turn pure states into mixed states. So, for example, if you take rho 0 as a 1/2, 1, 1, 1, 1, this kind of state, which is essentially a projection on the state up plus down. So it's equal superposition between up and down. Oh, well, and the projection. So okay, 1, 1, 1, 1. So upon evolution, as time goes to infinity, off diagonal terms will disappear. So you will just reduce everything to 1, 1, 0, 0, which is actually the most mixed state possible, okay? Just proportional to identity, okay? So this is how you can get mixed states dynamically, okay? Stochastic maps can give you dynamical mixing of states. Okay? It's not just this weird uncertainty in preparation of states. There are dynamical reasons for getting mixed states, okay? And we will finish it here, and we'll continue on next week because there are still a couple of things I want to touch on. Yeah. All right. So thanks for your attention and see you next week.